Welcome to P. Clark Calc, Practical Calculus for the Busy Math Student. And today we have a little request problem. It's an integral that involves both log rules and also exponential terms. And it's a little bit tricky until you've seen it once or twice, so let's have a look at it. Here we're presented with kind of a tricky integral. It's a rational function 2 divided by e to the negative x plus 1. And we might give it a thought that possibly we could use our general log rule for integration, which if you look at that, it states that we're looking for a fraction in the form du over u. But unfortunately, that's not the case here. We can tell pretty quickly that if u is equal to e to the negative x plus 1, if nothing else, the derivative is going to have a factor of e to the negative x in it. So there's no hope at all that this is du over u. So it's actually a bit of a tricky rewrite, and what you need to think about here is that this is technically a compound fraction. We don't always write it this way, or almost ever write it this way. We tend to use e to the negative exponent, but e to the negative x is equal to 1 over e to the x. And so the way to rewrite this function so that we can do the integral is to use the LCD method for compound fractions, which says that if we multiply the numerator and denominator here by e to the x, we get kind of a surprising result from that. So in its current form, we can't do anything, but when we take it and we multiply top and bottom by e to the x, here's what results. Our integral will be 2e to the x in the numerator. And then when we distribute e to the x through the denominator, we end up with e to the 0, which is 1 on the first term, plus e to the x. And don't forget your differential. So now we take a look at it and say, well, that looks a little bit more promising, because now we see that we have a factor of e to the x in the denominator. So if I'm going to call that the u, trying to use a log rule here, I know there at least must be an e to the x. So when I see the matching e to the x's here, that's one of the du indicators, is when you have identical e to the powers in a couple of places in your integral. So that tells us that it's time to write up the u sub and see what happens. If we're going with the log rule, u is the denominator, 1 plus e to the x, which means that du is e to the x dx. So this would be an almost du situation. We're off by a factor of 2 on the numerator, but simply enough, we could just use constant multiple rule. We'll take that 2 and remove it from the integral altogether, and that gives us what we need in order to use the general log rule. We've gotten this integrand down to a du over u case. So it's 2 times the integral of du over u. Remember, your dx differential is part of this du, right? We need that in order to have the differential du. So once we get there, it's kind of redundant at that point. It's going to be the natural log rule. So in the u variable, we have 2 times the natural log of the absolute value of u plus c. And then in the indefinite integral, if we start in u, we want to end in u. So we put our 1 plus e to the x back in there. Now, we could use the absolute value. We would not be wrong. But if you think about it, 1 plus e to the x cannot be negative. So in cases like this, you impress your friends if you omit the absolute value, because they're not needed. And we put our arbitrary constant on the end. And that's our solution. That's our antiderivative. One caution here. We do have, when you see a base e inside of a log, sometimes people want to jump to an inverse property. Natural log of e to the x is x, but we see a couple of terms in that loggerand. There's no log property that allows me to deal with multiple terms in the loggerand. So don't make up log properties. There's nothing you can do here. That's your answer. But it's ultimately a case of the general log rule, but with a bit of a wrinkle here, that originally this thing was not ready to go. It was not a du over u. And until you've seen it done once, I mean, it may not occur to you to do this algebraic step and multiply top and bottom by e to the x. But once you see that's done, you multiply through, and then the resulting integral is a du over u case. So we went ahead and did the antiderivative using the general log rule. Here at P. Clark Calc, we do practical calculus for the busy math students, but if you want to learn more about log integrals or integrals in general, you can find them on my calculus texts available on Amazon for the nice price. Till next time, I'm P. Clark.